Have you ever looked up at the stars and wondered if aliens look like us, or if they are silicon-based living stones? Many of us, inspired by science fiction, tend to envision aliens as carbon-based entities, similar to humans but with minor biological differences. On the other hand, some, including renowned science fiction author Isaac Asimov, imagine extraterrestrial life as silicon-based living stones. However, the confines of our earthly understanding may be too limiting. Could it be possible that life on other planets has evolved in ways we cannot yet comprehend? Before we blast off, hit the subscribe button and share it with your fellow space lovers. Now let's venture into the unknown together. The cornerstone of all life as we know it is carbon, an element that forms the very framework of our existence, thus constituting approximately 18% of our total body weight, or about 26 pounds. Carbon serves a structural role, creating a scaffold for vital organic substances like proteins, fats, carbohydrates, sugars, and even DNA. Carbon's significance extends beyond our bodies, playing a crucial role in plant life through photosynthesis. Each exhaled breath is rich in carbon dioxide, which plants use to produce oxygen and organic compounds such as glucose. Moreover, carbon dioxide creates a greenhouse effect, trapping the planet's heat and making life sustainable. Without it, Earth would be a frozen wasteland. Beyond biology, carbon is integral to our daily lives. It's in everything we see and touch, from clothing and medication to homes and devices. Its chemical versatility allows it to form complex chains with other elements, making carbon practically irreplaceable. According to astrobiologist Robert Hazen, an essential chemical element must form strong, long-lasting bonds and transmit information without being overly reactive. Carbon fits this bill perfectly, asserting its superiority as one of Earth's most crucial building blocks and beyond. However, one must consider if carbon is the only possible basis for life. What would happen if carbon were entirely devoid of the cosmos? Looking at the periodic table, the element directly below carbon might hold the answer: silicon. Silicon, the second most abundant element on Earth after oxygen, constitutes about 28% of the Earth's crust. This versatile element exists in various forms such as sand, clay, granite, and even precious gems like amethyst. Its wide range of applications has secured silicon's place as a vital element in our daily lives. It's found in the processors of our phones and computers, in cosmetic products as silicone compounds, and even in the aviation and construction industries, in the form of sealants and non-stick paints. But what about its role in biology? Researcher Milton Wainwright suggests that silicon may have played a part in the emergence of life on our planet. His studies indicate that silicon, especially if it originated from outer space, might stimulate bacterial growth even in nutrient-poor conditions. Wainwright hypothesizes that silicon-rich comets could have bombarded the early Earth, contributing to the development of bacterial life. Additionally, silicon is crucial for plant growth and development, acting as a protective shield against various threats and preventing dehydration. It also plays a pivotal role in human and animal health, promoting bone development, wound healing, and possibly reducing the risk of Alzheimer's and cardiovascular diseases. But why is silicon considered a potential basis for extraterrestrial life? This primarily stems from its chemical similarities to carbon. Silicon is located directly below carbon on the periodic table and, like carbon, is tetravalent. It can form bonds with 4 other atoms. This means it could potentially form complex, stable compounds similar to carbon. Furthermore, in 2016, scientists from the California Institute of Technology created molecules composed entirely of silicon and carbon, suggesting the possibility of silicon-based life. To truly answer the question of silicon replacing carbon as the basis for life, we need to understand life in biological terms and the criteria for its existence. Scientist Norman Pace defines life as the capacity of an organism to self-replicate and evolve to overcome challenges, requiring building blocks that can quickly adapt to new conditions and meet certain ecological criteria. As we know, life requires certain elements and conditions: oxygen, nitrogen, moderate temperatures, and water. Many compounds like salt are highly soluble in water, creating new bonds between different elements. Carbon is a critical part of this puzzle, having the ability to form a long, stable framework for the cells of water-based organisms. But could silicon, another element, also form the necessary connections for life? The answer seems negative. Silicon-based life at first glance appears improbable. However, this conclusion may be overly simplistic. While it's true that water is critical for carbon-based life, other solvents might theoretically support the emergence of life. For instance, scientists speculate that liquid ammonia, common on Jupiter and Pluto, could replace water as a solvent for life. Despite its toxicity, which might hinder the development of silicon-based life, this theory has not been fully explored. Sulfuric acid is another contender. While it's known to dissolve most metals, it could also serve as a medium for developing silicon. This suggests that silicon-based organisms might evolve on planets with a sulfuric acid environment, such as Venus. Furthermore, silicon can exist in cold solvents like methane and ethane, which become liquid at low temperatures, as on Saturn's moon, Titan. However, the slow chemical processes and limited solubility at these temperatures significantly constrain the emergence of life. Silicon's structural function also merits consideration. Like carbon, silicon can combine with elements essential to life, including nitrogen, hydrogen, oxygen, phosphorus, sulfur, and various metals. But there are limitations. Silicon doesn't bond well at moderate temperatures or in water, and the bonds it forms with itself are not as strong as those formed by carbon. This lack of versatility hinders the formation of large structures necessary for life. Interestingly, one element silicon readily combines with is oxygen, further complicating the potential for silicon-based life. On Earth, silicon is typically encountered in SiO2, essentially sand, making it challenging to separate the two components. This highlights silicon's lack of adaptability, especially when compared to carbon, which can form robust bonds with diverse elements. If silicon were to replace carbon in our bodies, we would be exhaling sand instead of exhaling carbon dioxide. Additionally, carbon plays an integral role in our nutrition. Our energy source is not food per se, but the compounds found within, such as glucose. Moreover, without food, another carbon compound, starch, stored in the liver, can replenish our energy supply. However, these bonds would be unstable with silicon, thus unable to sustain life. While it seems highly unlikely that silicon could replace carbon, the possibility for silicon-based life to evolve cannot be entirely ruled out. However, the proposition of an organism consisting exclusively of silicon with no carbon, forming intricate chemical bonds, seems far-fetched. Silicon-based organisms have not been discovered on Earth to date. Still, numerous plants and animals do contain silicon as a secondary component. Furthermore, our oceans contain diatoms, a unique form of algae with cell walls made of transparent SiO2. Although this doesn't classify them as silicon-based life forms, it does illustrate silicon's potential role in constructing a living organism. Regarding extraterrestrial life, a study led by Ricardo Gabato proposes that the ideal conditions for silicon-based life to develop include an absence of oxygen and water, temperatures exceeding 428 degrees Fahrenheit or below 32 degrees Fahrenheit, significantly higher atmospheric pressure than Earth's, and sulfuric acid or methane as potential solvents. Certain celestial bodies within our solar system meet some or nearly all of these conditions, namely Titan, Saturn's largest moon, and possibly Venus. Titan boasts numerous methane and ethane lakes and a nitrogen-rich atmosphere, optimal for the emergence of silicon-based life. Venus's surface is exceptionally hot and bears high pressure. However, the planet's yellow sulfuric acid clouds make it a potential candidate for silicon-based life. Hypothetically, silicon-based organisms could originate in the dense sulfuric acid clouds of Venus. However, given the abundance of carbon in Venus's atmosphere, such molecules would probably contain more carbon than silicon. Unexpectedly, the so-called carbon planets are another possibility for the emergence of silicon-based life forms. The only known exoplanet of this type is 55 Cancri e, 40 light-years from Earth. These planets are likely to orbit further away from their parent star, which could mean the presence of solvents suitable for silicon on their surfaces, and perhaps a lack of water. These carbon planets might also be rich in heavy hydrocarbons like butane, potentially facilitating silicon-carbon bonding. However, silicon-carbon compounds, silicon carbide, are highly resilient, leading to a slow decomposition process requiring much time and energy. Therefore, it would likely be an extended process even if life begins to form on a carbon planet. If we hypothesize that silicon-based life forms have existed for some time, how would we recognize them? While science fiction authors like those of Star Trek have painted a picture of silicon-based life forms resembling living stones, the appearance of these organisms may be vastly different. Since humans aren't covered in diamonds and diatoms look nothing like stones, it's clear that silicon-based life forms might not necessarily resemble our preconceived notions. In simpler terms, scientists don't know what silicon-based life might look like. They think that if it exists, it probably won't resemble us regarding chemical complexity or intelligence, so we can likely rule out the idea of meeting stone creatures. Finding such alien life, especially if it isn't technologically advanced, would be challenging, as we wouldn't know which molecules to search for. We're used to life as we know it on Earth, so our space missions usually look for structures similar to ours. The universe is so vast and varied that we cannot definitively say all extraterrestrial life across the billions of galaxies is carbon-based. This raises the interesting question: could life on other planets be within closer reach than we think? Maybe you can get answers to your curiosities in the coming videos, so don't forget to subscribe to the channel and share it with others.